Good afternoon, everyone. A warm welcome to all participants and students to the afternoon session of the conference. I am proud to invite Dr. Ajit to deliver his talk on quantum transport in engineered flatband lattices. Dr. Ajit is now working as an assistant professor in physics at Christ College Irinjalakuda. He has completed his PhD in physics from Central University of Kerala in 2016. His PhD thesis was on the topic of theoretical nano-optics and plasmonics. Immediately after that, he worked as a postdoctoral fellow at Institute for Basic Sciences, South Korea, from 2016 to 2018. He has also worked as postdoctoral fellow at ICER Bhopal from 2018 to 2021. His research interests include highly degenerate quantum systems, ultra cold matter, nano optics and plasmonics, and microwave waveguiding engineering. He has published 23 international publications and has written 2 book chapters to his credit. Connection വന്നു കേട്ടോ. Sorry for the connection problem. So, Dr. Ajit's research interests include highly degenerate quantum systems, ultra cold matter, nano optics and plasmonics, and microwave waveguide engineering. He has published 23 international publications and written 2 book chapters to his credit. I welcome Dr. Ajit to deliver his talk. Thank you.
Hello, am I audible?
Yes. Please continue.
Okay. Good afternoon, everyone. Good afternoon, Thomas sir. Thank you very much for inviting me to this program. Very much happy to give a talk. So probably I can start with the presentation.
Yes, sir.
Can you see my slide now?
Yes, it is visible.
Okay. So once again, thank you for giving me the opportunity. So it's really my pleasure to contribute to your program. Today, I would like to discuss about quantum transport in some specially engineered flatband lattices. Of course, the title looks too heavy, but I made the presentations in the level of a graduate student, not even in the master's level. But yeah, of course, I agree that everyone will be benefited to some extent, even if it's research scholars or faculties. But the level of talk will be in the level of graduate level. So I will be using some kind of stupid terminologies here, which will be kind of, to some extent, feel awkward because I want to keep everything very simple. Also, I will try to avoid all these big equations there and just discuss the matter in more detail. So to start with, we need to discuss about quantum transport, and the first thing is what I mean by this quantum transport. So the entire overview of the talk will be on this just one slide. Okay, so I have a lattice. You know that every material can be either amorphous or crystalline, but crystalline materials are somewhat important because you get some special properties from them. So crystalline materials will have lattices. You can consider one-dimensional, two-dimensional, or even three-dimensional lattices. So probably in the talk, I will be more discussing on one-dimensional thing to simplify everything. But yeah, of course, we can extend that to two-dimensional and three-dimensional lattices. But of course, one-dimensional lattices have some other important aspects which is not available in two-dimensional and three-dimensional also. So we have a lattice. So in the left picture, you can see some dots. So these dots are actually lattice points, or you can say that these are atoms in the crude way. I mean, it's just atoms. And then there you can see some lines there. Here, the lines do not represent any bonding. It's just represent that if I have an extra electron on one atom, it can move to the nearby atom. So the lines just represent the connections. We call it hopping. So the one electron can hop from one atom to another atom if there is a line present there. If there is no line present between two atoms, the electron cannot hop there. So that's the basic concept. So we will be following the terminology towards the end of, up to the end of this talk. Now, suppose that I have an extra electron in one of the atoms somewhere here. I showed the possibility of an extra electron by a different color here. So there was an atom here, so there is one more extra electron. The electron can come in different ways. Maybe I excited a valence electron to a conduction electron, or I just doped one of the atoms on the outer surface, and that atom contains an extra electron there, and that electron somehow hopped from one place to another place, and it's currently at here. So I give some time scale there. So at time t equal to 0, there is an electron there. Now the question is, what happens to the electron after a time greater than 0? I don't know what happens here, but at some time, I can say that there is a large area where I can see the electron. I can find the electron in a larger area. So the question is how I can interpret this. So one option is I can say that, okay, I transported the electron from, or not even me, I mean, the system transported the electron from one place to another place. So this is what I mean by a transport. And quantum transport means, of course, electrons are quantum particles. Size is very small. It behaves according to the quantum principles. We'll come to that later in a detailed manner. But this is what I mean by a quantum transport. But you will immediately say that we know about this because in your classrooms, because our syllabuses are too advanced in that sense, without going further into details, we just discuss about conductors, semiconductors, and insulators in a classroom. So you know that if it is a conductor, electron can move from one place to another. So then you define it in a fancy way, like, okay, you have a valence band, a below block region, and a conduction band above a block region in the energy scale. And probably you know already that, okay, if the conduction band and valence band overlap, then it is a conductor. The electron can move from one place to another place. A semiconductor, okay, there is a small band gap, so you need some energy to excite. The electrons will not move from here to here with smaller energies available for the system, and then we say that, okay, it's not possible to conduct it. But what are these bands? How these are formed? And what are the basic principles? We need to explore a little bit further to understand what is quantum transport. So we will go into that little by little, and we will explore this in the coming slides. Okay, so I can discuss a transport in two different ways, at least in two different ways. I mean, one is using the Newton's equation, right? I mean, I just need, so because my electrons will be transporting from one place to another, I can consider it as a particle. I can easily equation. I would say that there is a force acting on the electron and that force is allowing the electrons to move from one place to another. And I can write a Newton's equation there in terms of momentum. And if I know the force and moment, I can easily find out the position of the electron. Right. So R0 was some initial position, then okay, there's an acceleration, and as time goes on, position changes from one place to another. This is possible to some extent, but we already know that quantum particles need to undergo the uncertainty principle, which says that if I clearly know the position, I'm missing the accuracy in momentum. So to calculate the position, I need momentum, and to calculate the momentum, I need position. But if I am uncertain about simultaneously measuring these two quantities, I'm in a kind of dilemma how to find the thing, right? So that's why we need to move on to some new equations. Well, then the problem is that I cannot just pinpoint the electron. What I need to say is that I need to say there are some probability of finding an electron in a region. So I need to introduce a new function which will be actually telling me that, okay, this is the region where I see the electron. So I need a function. The initial step will be to define a function, and then we need to write an equation which is actually gives us the answer. Where is the particle at a later time? So yes, of course, we need a time derivative there to find out how the function changes with time. And then I'm not going in detail, but we know that the particle is moving when it has a kinetic energy. So I have some terms for the kinetic energy part, because if the particle is moving, then what I know is that the position is changing. So I can take a derivative with respect to position, and some uh, little bit manipulation, I can say that okay, the first term to some extent represent the kinetic energy term. Okay, then we already had a force with which the electron was, the force that electron was experiencing. So I can introduce a potential there corresponding to that force, and I can write the potential as the second term. So then the kinetic energy plus potential energy term will be there, which will be acting on a function, and the function will be changing over time. So I can solve this equation, and I can find this function psi as a function of position, and of course as a function of time also. So we call this function wave function. Now we need to connect this function to the probability of finding an electron. So the problem here is that this function can be complex, because I have a complex term I coming here. H cross is basically Planck's constant divided by 2 pi. Doesn't matter in our entire discussion. These are just parameters. So we so we wave function can be a complex thing. So probably should be real. So just the wave function, the wave function will give you a real number. So that can be taken as the probability to find the particle. So the particle is moving from one to another, pigmented to a particle, but after some time it is experiencing, I cannot find it properly where it is. So I say that, okay, it will be in a larger region. So I know that the function will be Newton's equation because of the you go to new computer is just a different equation here. Probably a matter equation, so it doesn't tell about this system. So use this equation to many systems. We will come back. But what is transport for me, or what is transport for the research I do? Okay, I have a lattice, so possibility of momentum. I know that it is moving in the x direction. I just say that, okay, I have a momentum and I have a value for that momentum. For that value, I just put a dot here. Okay, then I think about another possibility. The electron may move with a much larger momentum. Okay, and then in this axis, I put a dot on the right side. So the right side spot will be having a larger momentum than the left side spot. If it is the momentum is larger, I will put another dot there. If the momentum is larger, again larger, and I put another dot. Again, in the same way, I put dots in the y direction also. So basically, these are kind of forming kind of lattices then, because of some peculiar properties of this already existing lattice. So I have a new lattice. Now it's in the momentum space. Usually you call it reciprocal lattice in your terminology, but these are concepts. So whatever, we will come to some of the equations which define this lattice also. But these are kind of, so I have two lattices. One is the real lattice, where I have the atoms placed, and I have another lattice where I just have the momentums with which an electron can move. Now, if my lattice is larger here, kind of thing, but still I can say that, okay, how many dots are there? I can kind of a continuous still say. Now the question is, suppose I have this momentum corresponding to the first dot. The question is, what will be the energy for the I mean, sorry, so energy that which electron can be transported. Because if I need to transport an electron from one place to another place, it need to have some energy because it's moving, so it consists of energy. So the question is, what is the energy corresponding to this dot? I can calculate it. That we'll come to that also later, but let's go in the qualitative way right now. And for each points, I calculate the energy that is allowed, right? And then I can plot the energy as a function of these points on the x and y axis. So this will look something like this. So I have kind of an energy. For each point, I will have one point there. Then I'm just collecting all the points and I'm drawing like a picture like this. So the z axis or the third axis is the energy, and two-dimensional axis kx and ky. You can call it momentum or wave vector. It's up to you. Not much difference, but these are actually what momentum with which the electrons are traveling and what is the energy there. So this kind of a curve or diagram is called usually band structure, where you can say that okay, with this momentum corresponds to this much energy. So now if I take a value of kx or ky and says if I don't find an energy corresponding to that means that value, that means that the electron cannot propagate in the real lattice. So the electron can propagate in the real lattice only if I get a value for that kx and ky point for the energy. If the energy is not defined or is not possible, I cannot find a transport there. So the simplest way of expressing it is that the motion is defined by the energy allowed here. If I want to have a reduced energy for the same transport, it's not possible. Energy is fixed there. So more details about these things, the more equations, you can go to the famous textbook of solid state physics by Ashcroft and Mermin, and you get the entire mathematical complex natures of the equations and how you come to this kind of band structures. So far, do you have any questions? Because we will continuing this concept of band structure for a long time from here. Questions? Okay. Good. Now, coming to some linear chain of atoms here, I just have transport in one dimension. That means that momentum is also one dimensional. And I can put the momentums on a x-axis and find out what are the energies corresponding to each point. So basically, for these four lattice point, I will have just four momentum values, and I will have just four dots here. One here, maybe one here, one here, one here, and one here. Just four dots there, and I will have just get four dots here also. But if I increase the number of atoms here, I will be increasing the number of points also here. That means that I will be getting more points along this. So this curve is of atoms. So there are infinite number of atoms, infinite number of k points. So it's kind of a continuous looking one. The basic theory comes something like this. It is called the block theorem, right? So we have atoms there placed here. The same thing I can put it here. And now that there is electrostatic potentials coming there, so I can draw for each atom lines. I can take it in different parallel transfers or and it is what effective potential. Effective potential will be periodic nature. This is like this dot. This is the seen by an electron. So if the electron is somewhere here, it sees an attractive force there. Attractive means the energy can be less, potential can be less than zero. So it is a drop here. So electron here will be moved towards here. Electron here will be moved towards here because it's having a lesser potential. So that means that the atoms will be attracting the electrons towards it. So because of the periodicity of the atoms, you have the periodicity of the potential also. So again, I can write that famous Schrodinger equation for this system, but now the only difference is that potential term will be having a periodicity. Periodicity, capital X, will be the distance between these two atoms. So after every X distance, the potential still has the periodicity. The wave function that I defined in this Schrodinger equation will also be having that periodicity. So basically like this. So you really take the periodicity of this block function, potential, and you use a plane wave thing. So e raised to ikx will be sine kx plus I cos kx. You just take the real part, sine kx. So that is a kind of a sinusoidal wave. So this is a plane wave. and you just multiply the plane wave with the periodicity of your potential, and that can be your simplest wave function possible. Okay, and now the question is, what are the k values of atoms here? Now I have points on this having a periodicity much closer to the periodicity of, at least in the order of the periodicity of the atoms also. Now, if I take another point here, which is allowed maybe because of the second allowed k value, I'm getting a different sinusoidal thing because my wave function will be modified according to the k value I select. So the new wave function will be something like this. Okay, so if I want to calculate the probability of finding an electron, I need to square this thing because that's the square of the wave function is the probability. So if you square it, I get a peak here, again a peak here, again a peak here, again a peak here, etc. So that means that all the peak values will be the location for finding an electron. Okay, and this you are in a kind of PhD level or faculty level. This is all these uh, larger. I mean, you have a crystal lattice, you have a Bravais lattice, you have a unit certified. Then you call it reciprocal lattice, Brillouin zone. Then you come to Bloch theorem. So this is entire condensed matter course for you to some extent. Uh, After that, you will be just doing some calculations on magnetism or something. Otherwise, this is the entire condensed matter course for you. So this is basically the Bloch theorem that we discussed. Now the question is where I can use this transport and not transport concept. Of course, I can use that concept in lattices. So if you take just a silicon, I have a silicon lattice, and now I can take the allowed k values on the x-axis. Then I may have different directions. I call it lambda, gamma. Doesn't matter. Maybe one is x direction, one is y direction, one is xy direction. Then I can draw these energy values there. Uh, we had just one energy value here in the previous curve. Now I am putting more energy values according to the availability of electrons in the system. And now I have kind of a gap here, so you can see that some of the lines are here, some of the lines are around here, and then there is a region where there is no line at all. Right, it's completely it's upper, and then there is a conduction valence band here. So conduction electrodes are actually moving. So you can take one electron from the crystal, these kind of tubes there, silicon or something tubes, and then you shine a light through this tube. So a light goes from one side to another. So there's atoms stacked, and here it is just these tubes stacked there. So the principle is same. So it means that and light can go through it according to electrons. That means this crystal. It is also possible for ultra cold atoms also. Just cool the atoms and place the atoms in the vacuum according to your choice, and then allow excitation on one atom, and the excitation can move into different atoms. Same principle as this. So this equation can be used for ultra cold atoms. So the Schrodinger equation that we discussed, or the Bloch theorem discussed, doesn't stop to just lattices that we know for electronics, but it can be extended to different categories like photonic crystal, atoms, or wherever we have periodicity, we can use that theorem. Now, like previous case, we have, if you take one of the lines there, then I can say that okay, this line is having, so that is an energy value, and I can easily calculate the group velocity, the velocity with which the particle is moving there in the lattice, because the energy is a function of k. The energy value changes if I change the k value. So group velocity is basically dou E by dou k at anywhere. So that means that the group velocity is always greater than zero. You have transport. Line, it is having a curvy nature. So the velocity, if you calculate this, because there is a curvature, it's always zero. So the question is, have a system with velocity is zero. If I take S and multiply it somewhere, somehow, can I get a really flat lines there? And flat means that E by dou k will be zero. There is no zero. Because before going to such lattices, let me tell you one difference there. I can, I mean, what I'm looking at here is I'm asking for a group velocity 0. That means the particle is not moving at all. This can be also be done in a different way. I take a longer chain and I put an impurity there. And now extra electron may come from here to up to here. Because of the impurity, it may be just going back. So that means that if an electron coming from the left, then it may not ever reach the right hand part. Right? I mean, this is a blocking of the transport there. So this is again kind of group velocity 0 case, but I'm not talking about that now. I'm just asking a case where there is no impurity at all, and then still, can I get a group velocity 0? So this scenario is completely different, where you just put an extra impurity and then stop the electron from moving from one place to another. To design the lattice in a proper way. So I had a title as engineered lattices. So now what we do is, instead of going from one dimension, we go to a little bit quasi one dimension. So that means it's one dimensional in a chain. So the thing will be in the x direction. But instead of one atom per unit cell, you have now three atoms. So these three atoms will be repeating towards the right and left. So this is again a 1D chain. I would call it quasi 1D chain, but with three atoms there. So previously you just had one atom which was repeating like this. Now I just put three atoms instead of one atom there, and then kind of extend it in the x direction. Now I really, in most of the systems, I say that the electron will be mostly concentrating in the atom, and the electron will be here. But you're finding an electron in between the region will be very less. So the electron will be either on the first atom or on the second atom or on the third atom, not in between. Such cases, I mean, it's not valid for every system, but mostly in simplest system it is possible. In such cases, I can really define a tight binding model saying that the probability of finding the electron is there or atoms there. So then I can say that, okay, I have a wave function now, like previously, but I need to define a wave function for unit cell, not just for one atom. So for the nth unit cell, I call the wave function as A n, B n, and C n. So these are the sites A n, B n, and C n. So there will be some amplitude of finding the probability of the electron there. So that probability is discussed here. Then I can write this Schrodinger equation in this way. So the right hand part of the previous Schrodinger equation was IH equals dou psi by dou t. Now I can replace that with the energy with which the electron is traveling. And I have a potential term and I have a kinetic term. Now that means kinetic term means that the electron can hop from here to here. And I can put an extra term epsilon n, which means that if basically means that the atoms are of different nature, if possible. Epsilon n, so epsilon 1 will be here, epsilon 2 will be here, or epsilon 3 will be here. That means the three atoms can be different. But right now we are not considering that. So we call it Earnside energy to distinguish different types of entities of atom here. But we are not bothered about that one now. Okay, but the essential thing is that if I can solve this equation and I can find this energy as a function of the k values. In this case, I have three atoms per unit cell. That means that I can say that I have three bands there. Okay, so this is a kind of a simple calculation. So I'm not going to get too much details there, but you can go to this paper there. This will be, yeah, this paper there, physical review B. So you can see how this is worked out. But qualitatively, I can say that there are three bands. So, and one of the band, the center one, is really flat. So the energy versus k, if I take that thing, it's really flat. So the first derivative of energy with respect to k, dou E by dou k will be 0. So that means that the states, whatever points I get here, corresponding to that point, there will be zero energy and zero group velocity. So that means that the particle is not moving at all, right? So there are lattices like this. So this is called a diamond chip. So such lattices have this peculiar property that their energy is kind of really, their group velocity is zero. But there are two other lines there. So if I'm taking a state on these lines, then that means that they have a non-zero group velocity and the electron can transport from one place to another. But if I am taking a point here corresponding to this energy, so if I put an electron here and with the electron has an energy this much, then the electron will be just focused there. I mean, it will not move left or right. It will be just concentrated on. It will be trapped on some of the atoms here. So it will not transport. It will not be transported. So, so then what are the? Just a second. So what are the? First element history വിദ്യാർത്ഥിയായ stop here and take some questions. ഇതിലേക്ക് ഏവരെയും സ്വാഗതം ചെയ്യുന്നു. ഫസ്റ്റ് എമിനന്റ് ഹിസ്റ്ററി വിദ്യാർത്ഥിയായ ഇന്ന് ഉച്ചയ്ക്ക് 2:30 ശാവറ സെമിനാർ ഹാളിൽ നടത്തുന്നു. ഏവർക്കും സ്വാഗതം. താങ്ക് യു. Okay. No questions. Let me to conclusion that if I take a state here, for that k value, there is somewhere here. That means that the wave function will be located only on two sides. So that means that electron can be here or here. It cannot be localized here, and it is having no transport at all. So this is really the existence of something called compactly localized states, because the state or the wave function of the electron is just focused on just two sides. We can also create lattices where instead of having two this kind of curvy bands, you can have three flat bands also. A system having only flat bands, just like the red line, which you can have. You can also create systems which has just three flat bands. That means that the system is actually completely insulating. Okay. That means that if I put an electron on the such system, whatever energy value, whatever momentum I give to the electron will not move. It will be just focused on two sides. It can be here or here. Okay, I mean there is always an uncertainty. This is uncertainty principle. You cannot just pinpoint it. So it can have kind of a possibility that it can be either here or here. So that is the probability concept. But you can have all the flats band. I mean, bands really flat. That means there is also no transport. So we are just moving away from the concept of valence band, conduction band concept, but we are just moving to a simpler concept of what is insulator. So I can design a lattice which is completely insulating, but still follow the Bloch theorem. Right. Bloch theorem says that all the states can be extended, but it can be unique lattices which actually be really insulated at all. We have some properties there of these bands. We will come to that a little bit later. But there are not just one lattice. There were lots of lattices which actually can be found out where we have this flat band. So you can see that this is a lattice, and then there's a band structure corresponding to that here. And in every band structure, you get a red light like this. You can go to two dimension there. Then also you get the red planes there. Instead of lines here, you have now kx and ay, and now you see that there are just flat bands there. So that means that this is completely possible that you can design system. But the question is, what can we see in experience? There are no electronic systems till now found. Okay, so I had previously discussed that there is something called photonic crystals like this, pillars arranged, and a light is given from one side and allowed to propagate in that direction. And such systems, we have already found out that okay, these kind of localization is possible. So these are the CLS, the compactly localized states, which is just staying on a limited number of atoms. Not here, it is not atom; it is these pillars, and it is not extending anywhere. So there are lots of systems finding out where we can say that these kind of properties exist. We are still searching for system with electronic properties. Not yet we found it, but optical systems, there are lots of things. So why do we need flat band networks? The answer is that we have kind of highly degenerate states. Probably you don't know the terminology degenerate. The degenerate here, okay, water will be boiled. I mean, it will be the gaseous states in one place and in solid state in one place, or it will be mixed state in other place. Similarly, here I'm taking interaction versus disorder that I keep there, and I check whether this electron will be moving or not. So I'm really happy to get any kind of that. Your question is good, bad, nothing. Just be free and happily ask questions. Yes. So I believe that I didn't cover much things which is beyond your condensed matter course, at least in the PG level. I think in the graduate level also you study all these things. Mostly things change when you think about much more interactions of electron. If you have one more than, so maximum I put 2 electrons in the system. So if you have more than 2 electrons, like 5, 10, 15, 100 electrons, then the theory will not work in that much manner.
In turn can be used to study the structure and characteristics. So in this work, I have used the data from GALEX. GALEX is a space-based UV telescope which was launched by NASA in 2003 at an altitude of 600 kilometers. The foreground emission, namely this air glow and the zodiacal light, for deep observations. Similar methodology was also adopted for the medium observations and was estimated, which is just the paper is only communicated. And in this model, to find out the air glow, that is the foreground emissions I have calculated, I have subtracted this foreground emissions from the total GALEX count rate, and hence I have derived the diffuse background radiation. So let me just retell what is meant by this scattered by oxygen lines, etc., at the NUV and FUV band range. And this readings can be obtained from the GALEX data, and these readings are all in the spacecraft state files. And when I plot the photon count rate with time, I can see a bell curve. So there is a bell curve, there is a minimum of a bell curve. And for a single locations, as I told, for a single locations, so based on the different visits which are taken during different times, we can see that there is a variation in the baseline. That is the baseline. Here I am referring to the minimum value of each bell curve. So this shows that these are not due to the radiation from there. It is actually a contaminant. There are for this air glow. One is the minimum value for each bell curve, and that is known as the air glow constant. And the other one is the area under the curve. That is, you can see a bell curve. So the area under the curve is called as the variable air glow. So the constant air glow means the minimum value of each bell curve. I took many data and I finally developed this model, which is mentioned here. So as per this model, you can see that this baseline values is directly, or the air glow is directly proportional to the solar flux. As solar flux increases, air glow increases. Similarly, as sun angle increases, sun angle means the angle between the observation tile and the sun with respect to the earth. As sun angle also increases, the air glow decreases. So this is depicted in these diagrams. Then air glow variable. Air glow variable means here in this picture, it can be seen that as sun angle increases, starting from 87 to 173 degree, represented by this green line to this black line, there is a decrease in the curvature. So as the curvature decreases, the area under the curve also decreases. That means the air glow variable also decreases. So based on this observations, a model was developed, and this is the equation for this curvature, and this is the equation for the final model of after estimating the air glow using the air glow model and the zodiacal light, we can subtract these two values from the total count rate, and hence obtain the diffuse background radiation in FUV and UV. So let me now enter into the work. So these are methods. So the first way was the diffuse background radiation in FUV and NUV with optical depth. Optical depth means it actually represents the density of the gas and dust. As optical depth increases, the density of gas and dust also increases. That means as more dust is there, the radiation will also be large. So here also we are, as expected, we are getting a linear relation. As optical depth is increasing, so increasing. So these are the steps which I have taken, calculations just done to find out the optical depth at these regions. Similarly, I checked for the correlation between the UV diffuse radiations with IR infrared radiations. So they may be at different frequencies, but still there are contributions by the gas and dust in UV as well as IR, which can be compared. And that it may be, it is linear. So I checked for the linear relationship, and I got linear relations in FUV and NUV. So the IR values can be obtained from the Schlegel map, which is mentioned in this paper. And finally, the idea of radiative transfer. So the radiative transfer by interstellar dust grains is mainly composed of three things: the stellar distribution, the dust distributed picture. That is, galaxy is observing at this point, and star photons, stellar photons are, after traversing through a column of dust and gas, is finally captured by this galaxy detectors. So you can see that the stellar distribution plays a pivotal role. Similarly, the dust distribution, the characteristics of the dust distribution is also plays a vital role. And then the scattering function. So I made use of Henry-Greenstein scattering function. So this is the Henry-Greenstein scatter parameters of the interstellar dust and gas. For example, is called albedo or reflectivity. It will be 0 for dark grains and it will be 1 for fully reflecting grains. And G implies the scattering property. It will be 0 for isotropic case, and for forward scattering gains, it will be equal to 1. So since I ran a single scattering model. Single scattering model means I assume that the photons are scattered only once. So I used only low optical depth regions in FUV and NUV. And for all AG combinations, I found the reduced chi-square values. And these are the contour plots which I obtained for in FUV as well as NUV. Based on these plots, I can see that the minimum chi-squared values is reached for around 0.3 and 0.4 values of albedo. Even though phase function asymmetry factor is ranging for a large value, the minimum values were determined. And this minimum values were determined at a value of 0.3, 0.3 for FUV and 0.4 and 0.2 for NUV. And based on this in the single scattering model data were plotted along with the derived diffuse background data. And these are plotted with to check the galactic trend. So I can see that the galactic trend which I obtained is similar to that which is mentioned in the literature survey. So based on all these verification methods, I came to the conclusion that since it is having a positive correlation with optical depth, it is having a positive correlation with IR intensity as expected, and also I got the same galactic trend as mentioned in the literature survey. All these positive results shows that the success of this verification methods reinforces the accuracy of the airglow model, because I obtained the diffuse background radiation by subtracting the results from the airglow model from the total UV counted in both FUV and NUV. So these are the references that were used in this work, and thank you.
Thank you, Ms. Nilmi. We can have few questions. If there are no questions, let us invite our next speaker. Our next speaker is Ms. Soumya MS. She is an assistant professor at Department of Physics, Government College, Nedumangad, Thiruvananthapuram. Ms. Soumya, please present your work.
Thank you, sir. Can I share my screen?
Yes, please.
Sir, is this visible? Hello, sir. Hello. So can I start?
You can start.
Good evening, all. I'm Soumya, Assistant Professor, Department of Physics, Government College, Nedvangal, doing research under the Dr. K. Unnikrishnan, Retired Professor, NSS Hindu College, Changanasheri. Topic responses of medical. Before would I give some weather to particles and light chemicals, magnetic flux, magnetic nodes. But we are not affected by uh, these coronal mass ejections in most of the cases because of this Earth's magnetosphere. You can see the picture of this magnetosphere here. The magnetosphere deflects all the charged particles and field from. But in some cases, when the intermagnetic field is southward, that is when the Earth's magnetic field and the solar magnetic field from the Earth is coming opposite to each other, then a process called the magnetic reconnection happens, and a large amount of heat and momentum and energy transfer takes place between Earth's field and intermagnetic field. This will cause disturbances, temporary disturbances in the Earth's magnetosphere that we storms, geomagnetic storms. Of course, a large amount of particles and energy enter into Earth's magnetic field. We know that ionosphere and magnetosphere are electromagnetic coupled to each other. Electromagnetic regions of southward, then only this magnetic reconnection happens. Then charged particles enter into the geomagnetic field, and magnetic storm happens. So magnetic reconnection is the process, main physical process behind these geomagnetic storms. I would like to mention one of the very historical occurrence of geomagnetic storm. It is the Carrington event in 1859, and this is the highest storm occurred ever in history. The disturbance storm time index, or DST, is the measure of that is the index or parameter we use to measure or indicate the strength of the storm. If DST value is less than 50 nanometers, we take it as a geomagnetic storm. When it is greater, then what happens when this geomagnetic storm occurred? A large amount of charged particle enter into the Earth's atmosphere or Earth field. Then a large amount of geomagnetically induced current will flow through some telegraphic lines and all that, and also radiation hazards too. And most common these geomagnetic storms are affected by higher latitude countries. In India, we are located in equatorial region. We are not much affected by this in the ionospheric parameters. This will in turn make disturbances, or we call it as distortions in the signals, satellite signals. These distortions are called scintillations. So whenever these magnetic storms happens, these scintillations will we have to monitor and rectify these scintillations whenever we pass signals through ionosphere in a geomagnetically disturbed. For this, we have to continuously monitor and study these storm time and quiet time variations of these processes. A lot of projects are happening with the European Space Agency, NASA, or SOHO. A lot of programs are running to continuously monitor these extreme space weather events. So the disturbances in geomagnetic field during storm time are being mapped to ionosphere, resulting in ionospheric storms. There are a lot of parameters that we use to represent the ionospheric conditions for a particular time. They are virtual height, peak electron density, total electron content, critical frequency, etc. Critical frequency is the frequency, the maximum frequency at which a signal can be transmitted to the ionosphere. So whenever this happens, a storm event happens, this may invoke fluctuations in these parameters. So we have to continuously monitor and study these parameters during quiet time and storm time to forecast the problems related to these extremes and Okinawa. Here, this is the latitude and longitude of the stations I selected. All these are mid-latitude stations, from which Wakana is a comparatively higher mid-latitude station. These are the storm events I selected in this study. These storm events are extreme severe storms. You can see that the DST values are greater than, the modulus of DST value is greater than 250. Or all the 6 events I took were very severe storm. 23rd is the location of the event in the time series. In that analysis function it, and by continuously varying the values of the scale parameters, we obtain the CWT coefficients. We plot the CWT coefficients, and we get a picture in the amplitude versus scale of parameter. And by analyzing the graph or the picture, we can obtain some information from the about the signal. Here we used mode and is given by psi t equals pi raised to minus 1 by 4 e raised to I omega 0 t e raised to minus t square by 2. A signal produced relative values, IMF calculating the wavelength parameters, we can obtain some information about the variations. I would like to explain my results based on one event. It is I studied many events, particularly which shows the strength of the storm. You can see that on 8th November, the DST value decreases to minus 263 nanotesla. So the value decreases. DST value measures the average value of horizontal component of Earth's magnetic field. Storm happens, the horizontal component of Earth's field decreases and decreases. Here, the particular event, its value decreases to minus 260. That at the same time, the IMF BZ, that is the interplanetary magnetic field, also goes negative for few hours. Then the DST value also decreases. Also, KP index is also the storm. Whenever the KP index is greater than 5, we consider it as a storm event. In the right panel, the ionospheric parameters are shown in the right panel. The critical frequency, which is